Now let's look at the second example problem in topic 1. So this is a lead code problem called find the pivot index. So again, we are given an array of integers, and the pivot index is defined as the index where the sum of the number to the left of that index is equal to the sum of the number to the right of the index. So let's look at this sample. We have an array of 6 elements. So the pivot index in this case is 3, because 3 points to the this array element 6. Because to the left of 3 we have 3 elements, 1, 7, and 3. They add up to 11. To the right of this element we have two elements, 5 and 6. They also add up to 11. So they are equal. Therefore, this is a pivot index. So the question asks us to compute the pivot index, and if none exists, we return -1. If there are multiple pivot index, we return the leftmost pivot index. So this is natural solution. Is let's just try every single index and see whether it is a pivot index. If it is, we will return that. So we have an outer loop that goes from all possible index from 0 to n-1. And within the loop, we compute the left sum and the right sum, where the left sum computes the sum of all the numbers to the left, and the right sum computes the sum of all the numbers to the right. So when they are equal, we will return the index. So, and if the loop ends without us returning any index, then that means pivot index does not exist, so we return -1. So the question is, what is the time complexity of this approach? And given the time complexity, then how to improve that? And again, the way to improve it is to figure out what computations are repeated and figure out ways to avoid that repetition. So think about that. So the time complexity is n cubed because the loop here from line 4 to 7 is executed n times, and this loop contains 2 separate loops. Together they will execute, they will basically go through the n element again. So they will go through some number of elements to the left, some number of elements to the right, but together they will basically add up to n elements. So we'll be doing operation that's linear to n inside the loop, and because the loop goes through n times, so the total number of operations is some constant times n squared, so meaning that the complexity is big O n squared. So, and the repeated computation, it's pretty obvious. We are keep adding up these things, to the array elements. We are keep adding them up. So in order to avoid that, we can we can sort of compute the sum fewer number of times. And in this case, we have a solution that takes time, big O n, and it takes the big O1 extra space. So in addition to the array, we only need to store a few additional variables. We don't need to store something like make a copy of the array or store something that's about the same size as the array. So the way to do that is we compute 2 things. We first compute the total sum, and then the second time we scan through the data again, we will compute a running prefix sum. So let's look at the code. So the line 3 compute the total sum, and then the loop from line 4 to 7, it goes through all the elements, and then it compute the prefix sum. So the p sum stands for prefix sum. Prefix sum, so as you can see, it will keep adding a new element. So at line 5, the prefix sum will be the sum of all elements with the index less than I. So from that and the total sum, that gives us sufficient information to tell whether I is a pivot index or not. So think about what code should go in here in order to make the code correct. Going here meaning on line 5 to make this correct. So here is a code that would work. So you can do it in other way. This will be equivalent. So essentially, if the prefix sum plus the current value plus prefix sum equals total sum, that means the sum of the element to my right must equal to prefix sum. Because the sum of the element to my right must be a sum minus prefix sum minus num size. So if that equals prefix sum, then I is a pivot index. So then the complexity of this approach is linear, because we essentially just go through the array twice. And every time for every single element, we just perform some constant operation. So the complexity is linear in N. So we are able to reduce quadratic to linear by using this rounding prefix sum and the total sum. So the key thing that I hope you will remember from this problem is there is this concept of prefix sum, where it's defined here. So prefix sum, given an array of n elements, there are n plus 1 prefix sums. So the first guy is just 0. And then the next guy is the first element, and the next guy is the sum of the first 2 elements, and so on. So in this problem, we use the prefix sum, but we didn't, we sort of keep a rounding prefix sum. We didn't store every prefix sum because it's not needed. We just need to compute everyone and then use it. But in some problems, we need to store these prefix sums in an array, and this will greatly help some problem. I guess one sort of standard problem is, suppose I have a given array and I keep asking you sum of some range. So one query may come in asking you, what's the sum from the 4th to the 10th element? What's the sum from the 5th to the 11th element? So knowing a prefix sum, we can compute this range sum, because every range sum will be the difference of 2 prefix sum.